Hi Psych 302. So this is a little bit of a different video than we're used to, but what I'm going to do here is just sort of go through an overview of some of the examples that you saw in the online textbook, My Statway, because sometimes it's really hard to just read a big bunch of text about statistics, so I thought we'd walk you through it. All right, so this one is about Melanie and her cell phone data. She wanted to test these download speeds, right? And so she saw this ad that said, on average, it takes 12 seconds to download a song, a 3-minute song in Los Angeles. And she's like, wow, that seems pretty fast. I don't think it's that fast when I usually download songs. So she tried it. She tried it with one friend's phone. And it turned out that for this first song, it took 13 seconds to download. And so she's like, 13 seconds? Well, maybe that was a fluke, right? Maybe the next time it'll be 11 seconds or 10 seconds, right? And then it'll average out to be 12 seconds, right? And so she did this 45 times. And when she did this 45 times, on average, the average was 13.5 seconds. Right? So that means, a bunch of songs were like 15 seconds, 16 seconds, 14 seconds, and a bunch of songs were 12 seconds, 11 seconds, 10 seconds, right? There's a little bit of jiggle. There's variability there. The question is this from this population? Right? If this is the mean of the population, could this sample have come from that population? Or is it sort of unlikely to have come from this population, right? Now, to think about this question, we're going to go back to our distribution triad. After all, distributions, this is what statistics is all about. And really, we want to know, hey, we have this sample of n equals 45, right? And the mean download time was 13.5. And we're saying, well, what's the population that the same sample came from, right? That's what we really want to know. What's the population? Right now we don't really know, right? But Melanie has seen an ad for this population. And in the ad, the company, I'll write it up here, company claims that the average download time is 12 seconds. But Melanie looks at the sample and says, is that sample likely to have come from that population? This is when you want to do a hypothesis test. So, in a hypothesis test, for one sample, since she only has one sample, we can't go directly from the sample all the way up to the population. We can't just make a conclusion like that, right? So, instead, what we're going to do is pretend that that really is the population, and then create a bunch of samples from that population. And we're going to call that a sampling distribution, or SDOM, right? These are all the possible samples that could have come from that population. And then we're going to compare this sample to all these other samples that could have come from that population to try and see, is that really the population? Could it be? Or is it unlikely to be the population? All right, so step one, we're going to start with the null hypothesis and the alternative hypothesis. This is going to be a little bit different from the book because in my class, as in the real world, you're always going to do a two-tailed test. The book example does a one-tailed test, but I want you to do a two-tailed test. It's just going to be more useful to you. The null hypothesis is this, that the population, the mu is 12. Okay, we'll go with that. We'll say, company, sure. We buy your claim. We'll see. We're going to test that hypothesis out, right? And so the alternative is the mu is not 12, right? And judging from our sample, we would guess, maybe mu is bigger than 12, huh? All right, so what does it mean that we're going to test out this null hypothesis? Well, this means that we are going to test out the idea that our sample came from this population and it was drawn randomly from it, right? Remember our null hypothesis sort of drawing? Here, let me move the camera down. All right, so here's this pool that I'm drawing from, and these are all the different ways that you could, different times that you could download songs, right? So from all over Los Angeles. And the company is saying that the mean of all those download times is 12, right? So every individual in Los Angeles downloading 3-minute songs, on average, it takes them 12 seconds. Now, what is the likelihood that this sample that we have here, where x bar equals 13.5, was randomly drawn from this sort of population, right? So imagine we have all these songs being downloaded, right? And imagine taking 45 of them out. What's the likelihood that this would be the mean that you would get, right? And so this is sort of a schematic picture of our null hypothesis. But make sure you could explain it with words. All right, so now let's move on to alpha. So our alpha is really saying, okay, so how likely or how unlikely does this thing have to be, right? So it has to be pretty unlikely for us to reject this null hypothesis. We have to have a 5% or less chance that this sample was randomly drawn from this population for us to reject this as the null hypothesis. Right? So let's refer back to our distribution triad to see where we are. All right, so we would really like to make some sort of inference from the sample to the population, but we can't make that directly. So I'm going to put an X there. Oh, I wish we could, but we can't. Okay. So we've said, fine, let's say that this is the population and test it out. And that's why this is called a hypothesis test. We'll say, okay, fine. Let's say this is a population. We're going to draw all the possible random samples from this population. Now, that's this arrow right here. But we don't really have that population, so we can't simulate it. We can't pretend to draw 45 samples randomly over and over again. So are we stuck? Nope. What do? We use the central limit theorem. Right? And so that's what we're going to do to create the SDOM and set our decision stage. All right, so here's our SDOM. So I'm going to write SDOM on the side so that I could always keep track. And these are all the possible means that could have been drawn from our null hypothesis population. So I'm going to write that up here. Mu equals 12, right? So from that, I can say, oh, I know the mean of this sampling distribution thanks to the central limit theorem, right? Because the mean of the population is the same as the mean of the SDOM. Now, what shape is this SDOM? Well, I don't know if it's normal because they didn't give us sigma, so it's not a Z or normal distribution. Maybe it's a T distribution. Well, in order to use T, we know that sample size has to be fairly large, and sample size is N equals 45, and that's pretty large. So we're safe in assuming that this is a T distribution. Great. So we're going to use this as this. We're going to call this shape a T distribution. Now, can we find out the standard error? Because in a SDOM, we can't figure out any probabilities unless we know standard error, right? And so let's figure out the standard error. And the book already did it for you, but I want to just walk you through it. So since this is a T distribution, we know that we only have S. And I think S was 3.2, right? But we don't want S. S is just the standard deviation of the little sample of 45 that we took. Instead, we want to know the standard deviation of this SDOM. We want to know that right there, the size of that smoot, so to speak, right? And so, to find standard error, that would be 3.2 S divided by the square root of 45. All right? And so you could do that on your calculators if you want. So that's going to be 0.48. 0.48. So about half a second. So one standard deviation out from the mean would be about 12.5 seconds, right? And then two standard deviations out would be 13 seconds. So already we know our sample mean is 13.5, so that's going to be like way out here. So as I said in class, I'm going to try to put the sample in green. So you know the sample mean. So I'll write 4 here just to keep track of our sample stuff. So we know the sample mean. That's 13.5, right? Now what's the sample t? Well, you could calculate it. You could have SPSS do it, right? And we'll go through the formula. But here's the intuition I want you to have. So basically, where is 13 on this SDOM? Well, it should be, over here somewhere, right? And if this is about half a second, then 2 of these would be like a whole second. So that should be about 13. And then 13 and a half is another one. So it should be almost 3 standard deviations out. So it should be like somewhere here. That's what I'm guessing. Almost 3 standard deviations out. Right? But in order to know how many standard errors out, standard deviations of the SDOM, we could do the sample t formula, which is take that distance between 13.5 and 12. So this is the distance in raw seconds, right? So it's 1.5 seconds difference, right? But then we want to see how many standard errors fit in there. How many smoots, right? 3.14 standard errors, right? So if we go back to our picture, it's like here's one standard error out, here's another standard error out, here's another standard error out, and it's not quite a full standard. It's like 3 and a 0.14. Sorry, my drawing is a little crooked. All right, so see how it's not quite a full standard deviation out, it's just a 0.4 of a standard deviation out. So there's one standard error, another standard error, another standard error. So 3 standard errors and 0.4 of a standard error. And that's what this sample t is telling us, right? So at that point, what we want to know is the p-value. Now, what the book has done is it's done a one-tailed test. So it only gives you this little part. This little area, right? And you get an area, a p-value of 0.0015, right? 0.0015. Now, SPSS will give you a 2-tailed p-value. That means it's going to take that and also give you the symmetric distance on this side, the area that's symmetric on this side, and just add them together. So you could just essentially take this little figure, 0.0015, and multiply by 2, because there's 2 tails, right? And so in SPSS, you should get a p-value of p equals 0.003, right? So let's interpret that p-value. So that means that the probability that this sample, or a more extreme sample, like way higher or way lower, the probability of that kind of sample being drawn by chance is 0.003, right? So that's less than 1%. In fact, it's just 0.3%, right? That's very, very small chance that this sample was drawn randomly from this population up here, right? So step 5, which I could write down right here, just to write it down, is we reject the null. We reject the idea that this was a sample that was randomly drawn from this sort of population. So now let's return to our distribution triad. So what we did was we got a sample but we want to know, was the sample likely to have been randomly drawn from this population? And so we drew all the possible samples from this population through the CLT and created a sampling distribution of means, a whole bunch of samples. And we said, hey, how does this sample compare to all these other samples? And what we found was this sample is unlikely to have come from, unlikely given all these other samples, right? Okay, so the probability that this sample came from this sort of population randomly is 0.003, right? It's pretty low, right? And so what we do in our final step of hypothesis testing is we reject this idea. We reject it. We say, this is probably not the population that this sample came from. So maybe it's another population. Maybe the mu is not 12, right? Don't you wonder, well, if it's not 12, what is the mean of that population, right? That's where confidence intervals comes in. In confidence intervals, we're doing a very different thing. We're saying, here's the sample, and now I'm going to erase this part because we don't think that's the population, but we have this question mark there. What is the population that it came from? Now what we could do is what we did in class, where we just pick. We're like, well, maybe 14 or maybe 13 or maybe 13.1 or 13.49. We could pick a bunch of different populations and test them all out. Or we could calculate a confidence interval from the sample that tells us, here are the ranges of different populations that this sample could have come from, and we have 95% confidence in any of those means that are in that range. All right, so I've just drawn a fresh drawing of our distribution triad, and now we're going to just sort of think about confidence intervals. So let's say Melanie has this issue, right? She just did hypothesis testing, and she was like, dude, I don't think that this cell phone company is telling me the truth. I don't think that 12 is the population mean. But then what is it, right? All she has for sure is her sample. And I'll write down the sample mean again so we don't forget. X bar equals 13.5. So that was the mean of her sample. And she had 45 different downloads in her sample, right? And so she's saying, well, I guess based on this sample, if I had to just guess what the population mean was, I guess my best guess would be 13.5, right? I mean, if the population was the mean was 13.5, then definitely I would get a sample that was 13.5, right? Well, but that's just one number, and I'm not totally sure that it's 13.5. It might be 13.6, 13.4, 13.51, 13.52, maybe even 14, right? And so we really want to know a range of different options, right? And so what we do for confidence intervals is we take as our best guess of the population is the sample mean, right? The best guess that we have for the population mean is the sample mean. After all, we really did get this sample, so maybe it was drawn from a population where mu equals 13.5. But we also want a little bit of spread. We want to go sort of up and down. There's a little bit of error in both directions. And so what we do is we create a sampling distribution of the mean. And through that, we could calculate the confidence interval. And I've already calculated it for you. So here's this confidence interval. And the confidence interval says that the mu of the population, based on this sample, is we're 95% confident that it's between 12.54 and 14.56. Right? We're not 100% confident, but based on this sample, we're pretty confident in saying this is probably where our population mean actually lies.